Time for us to do some practice involving Riemann sums, which says what? Well, we're trying to estimate the area under a curve from some starting point A to some ending point B. And we'll do it by saying, ooh, it kind of looks like a bunch of rectangles. Well, approximately. And so it's not so bad. It's just saying, hey, think about the area of each piece. There's a length, there's a height. All right, add the pieces up. Life is good. And so, not so bad. Really, it just takes practice, which means you should practice. So if you're following along with the video, make use of the pause button. See a problem that you like, pause. Try it yourself first. See how far you can get. And if you ever have any questions or concerns, no problem. Unpause, and we can work it out. So, let's begin. Our first problem. Estimate, and remember, Riemann sums are really estimates of the area. They won't find the area exactly. That's okay. Estimate the area under y equals 4x squared, where we go from 0 to 4, by Riemann sums with 4 equal-sized intervals, and using each of the following. Left endpoint, right endpoint, midpoint. So what's going on here? Well, sort of the picture we should have in mind is we have our x and y, and then 4x squared, it's a parabola, it's going to go up. And we're going from 0 to 4. So let's say here is 4. So, in some sense, what are we trying to estimate? Well, what we're trying to estimate is this region here. So the area under this curve. And what are we told to do? Well, we're going to do it by splitting into 4 parts. So when we say 4 intervals, what we really say is we're taking from 0 to 4 and breaking it up. Now, from 0 to 4, that's length 4. If we split into 4 equal parts, each part has length 1. So in particular, we say, okay, 2, 1, 3. Now, what we're going to do is for each part, get an estimate of a rectangle. So the question becomes, what rectangles to use? In other words, what's the height? So that's where the difference is between left endpoint versus right endpoint versus midpoint. So let's talk about left endpoint. So for left endpoint, it says, if I take an interval, go to the left-hand side. So what do we have? Well, we would say the following. We would have, for the first interval, that goes from 0 to 1, we would say, just for reference, I'm going to call this here f of x. So it would be, for the left, we would have f of 0. So that's the left end times 1. So there's a height, there's a width. This is sort of our delta x, which is the width in the bottom. For our second interval, it would be f of 1 times 1. Our third interval, f of 2 times 1. And our fourth interval, f of 3 times 1. Now we just evaluate, and okay, f of 0. 4 times 0 squared, 0. Of course, times 1 gives us 0, plus f of 1. 4 times 1 squared, well, that's 4. F of 2, 4 times 2 squared. Well, that's 4 times 4, 16. F of 3, 4 times 3 squared. And that's 4 times 9, that's 36. So 0 plus 4 plus 16 plus 36, giving us a grand total of 56. So picture-wise, these are rectangles where we go up to the left-hand point. So there we go. And in particular, we say, ooh, so this is definitely below. Because if you look at the rectangles, they fit underneath the curve. It's a lower estimate. All right, well, that's one thing we have to do. Well, let's go to our next one. our right endpoint. What does that mean? It says if you pick an interval, go to the right-hand side instead of the left-hand side. So for the right, what do we have? Well, for the first interval, the right end would be at 1. So the function at 1 is the height, width is 1. For the second interval, function at 2, because 2 is the right endpoint. Third interval, it'll be 3. And for the fourth interval, it'll be 4. All right, well, f of 1, 4 times 1 squared, still 4, hasn't really changed. Plug in 2, 4 times 2 squared, still 16. Plug in 3, 4 times 3 squared, 36. You'll notice, wow, these match. Well, yeah, because they're matching in the middle. It's the ends where they disagree. Finally, when you plug in 4, all right, 4 times 4 squared, 4 times 16, 64. All right, well, okay, so that's 20. When we add those together, that's 100. So altogether, 120. All right, wonderful. In terms of the picture, when we use the right endpoints, we're using these big rectangles. And now we say, all right, whatever the real answer is, it's somewhere between 56 and 120. That's a pretty big range. And so there's room for improvement. All right, so what's the last one? Well, the last one is midpoint. Well, how does that work? Well, for that one, it says, look, if I'm on an interval, I'm going to go halfway in between. So it's not the left, it's not the right, it's the center. Okay, so halfway between 0 and 1. Half. So that'll be f at a half. So that's f at a half is the height that we're going to use for the first interval. So times 1. Halfway between 1 and 2, well, the easy way to do it is just add 1 and 2 and divide. So 1 plus 2 is 2, and then divide. That would give us 3 halves. Halfway between 2 and 3, 5 halves. Halfway between 3 and 4, 7 halves. All right, well, what do you get? Plug in a half. A half squared is the same as 4 times a fourth, which means that this will give us 1. 3 halves squared is 9 fourths, times 4 will be 9. 5 halves squared, 25 fourths, times 4 leaves us with 25. 7 halves squared, 49 fourths, times by 4 gets us to 49. Okay, so what does that turn out to be? Well, okay, 1 plus 9 is 10, plus 25 makes 35, plus 49 would make 84. Okay, and then again, picture, go into the middle, go up. So those would be our rectangles. Now, which one of these is the correct answer? Well, the answer is they're all estimates. Now, the real thing you might be wondering is, which one's the better estimate? Well, because we see that the left is definitely a lower and the right is definitely an upper, midpoint probably feels pretty close to the truth. Now, we're not saying that the midpoint is the truth, and we don't have the tools yet, but we will soon to actually find the answer explicitly, but it's a reasonable guess. And the good thing is, of course, is we see, look, we knew that left was definitely a lower bound, right was definitely upper bound, so it's good that the midpoint is somewhere in between. All right, so there we go. That's the flavor for what we're going to do. Break things into parts. What happens for each part? Add it up. Life is good. So, now, estimate the area under the curve y equals the square root of 25 minus x squared for 0 less than or equal to x less than or equal to 5. And you use Riemann sums with 5 equal intervals to give both an upper and lower estimate for the area. Now, we should try to understand. Do we recognize that curve? Y equals the square root of 25 minus x squared. It feels familiar, like we've seen something like that before, because it's familiar. We've seen something like this before. It's part of a circle. In particular, it's the circle of radius 5. All right. Now, if you're not sure, what? Why? Square both sides. That's y squared equals 25 minus x squared, or x squared plus y squared equals 25. Now, what's going to happen? We're trying to get upper and lower bounds for the area. So, what can we do? Well, we can think about the picture here. We know there's going to be 5 equal intervals. Now, we almost always, when we're doing Riemann sums, work with equal intervals. Technically speaking, you don't have to. So we'll specify that they are equal. But generally speaking, if you're working with Riemann sums, you should anticipate equal. So because we're 5, well, I'm going from 0 to 5. So that would say, all right, that should break things up in a nice way. Namely, we can break things up where step size 1. We can think of it 5 minus 0. That's the total length between 0 and 5. Then divide that by 5, how many pieces we're breaking up into. So we can say, aha, our delta is 1. So if thinking of delta, the change between consecutive points is 1. Now, we'll do lots of examples where, yeah, delta is 1. But remember, it doesn't have to be, so don't forget it. You always have to account for that. So now we start saying, okay, let's suppose we want to work with the upper bound. What do we need to do? Well, we say for each point, what we'll do, or rather, not for each point, for each interval, right? Because we're splitting these into little strips. And what we want to do is say, okay, if we're doing an upper bound, what we want to do is put a rectangle over each strip where the curve, in this case the circle, is completely inside the rectangle. And so, what's the highest point? Now, if we look at the behavior of the curve, we see it's starting and going down. So, because it's going down, we say, all right, the behavior says, if I want the highest point, I'm going to choose a point on the left-hand side. So, I'm going to choose the left endpoints. That will give me the upper bound. So the upper, in this case, left, and mind you, it's only left because of the nature of the curve. If a curve is decreasing, higher values occur to the left. On the other hand, if we had the opposite, which is to say what? Well, if the curve were to be increasing, then the higher values would be to the right. So just be careful. Okay, so what do we have? Well, our Riemann sum, we use the values of the function as the heights times the widths, in which case our widths are 1. So it'll be function at 0 times 1 plus our function at 1 times 1 plus our function at 2 times 1 plus our function at 3 times 1 plus our function at 4 times 1. And you'll notice another thing here. See how many terms we have? 5 terms. What's special about 5? Well, because it says here, 5. So however many terms you have should match the number you're trying to find. Because you should have 1 term for each rectangle. Since we had 5 terms, we should have 5 rectangles. Now, well, we clean up. Plug in 0. 25 minus 0 is 25. Square root of 25 is 5. Plug in 1. That would be 25 minus 1, 24. So, all right, that's something. Plug in 2. 25 minus 4, 2 squared. Square root of 21. Plug in 3. 25 minus 9. All right, well, 25 minus 9, that's 16. Well, that's actually kind of a nice number. That would be 4. Plug in 4. 25 minus 16 is 9. Square root of 9, that's a nice number, that's 3. And so we can say, all right, now we could if we wanted to, and why not? 5 plus 4 plus 3 is 12. 24 is divisible by 4, which is a perfect square. So we could pull it out. That's the same as 2 times square root of 6 plus square root of 21. So that's an upper bound. Now, what if we want to do a lower bound? Well, for a lower bound, similar philosophy, right? Now we want to get rectangles completely inside the curve. So, because our curve is decreasing, and we want to choose the lowest point for any interval, it's really going to be, in our case, the right-hand side. So, what do we see here? Well, that says our picture is going to be a little bit different. So, we're going to get, for the first interval, f of 1 times 1. Second interval, f of 2 times 1. Third interval is f of 3 times 1. Fourth interval is f of 4 times 1. And the fifth interval is f of 5 times 1. All right, well, a lot of these we've done, right? At least these in the middle match. The only one that's new is the descend one. So square root of 24, that's when you plug in 1. Square root of 21, 4, 3. And when we plug in 5, 25 minus 5 squared is 0. So we're going to get 0. So what do we end up with? Well, we end up with 7 plus, and then again we can pull out a 2 in the square root of that. So that would be 2 square root of 6 from that 24, and the square root of 21. And there we go. These are upper and lower bounds. Now, we do know the actual value because it's 1/4 of a circle of radius 5. So in between these two numbers is 1/4 of pi 5 squared. So in other words, if you look at whatever 25/4 times pi is, 25/4 times pi is in between these two values. Now, you might say, there's a pretty big gap here of 5. Can you improve it? Well, yeah, you can. What do you need? More rectangles. More rectangles, higher precision. Higher precision, better estimates. But of course, that also gets into doing lots and lots of addition. And at some point, we don't get very excited about adding lots of numbers together. Now, the good news is your computers, they love it. They love adding numbers together. So they would love doing better estimates. So it's one of the things that computers were built for. In some sense, computers were almost exclusively built for things like adding. They're adding and multiplying. They love that. It's their favorite pastime. They couldn't be happier. So a lot of the things we talk about are just to sort of get our ideas going. In practice, we turn over to the computer and let that do all the hard work. All right, to our next problem. Use a Riemann sum to approximate the area under the curve of the function 17 divided by 1 plus t to the 4th. Ooh! And now we're going to go from -5/2 to +5/2. And we're going to use a partition with 5 equal parts and choosing the center point on each part of the partition. Well, All right, let's think about our number line. What's happening here? We're going from -5/2, we're ending at +5/2. All right, so how far apart are those two numbers? Well, you can take the difference. 5/2 subtract -5/2 is 10/2. So they're 5 apart. Oh, that's very convenient because we have 5 equal parts. So since it's 5 apart, well, 5 divided by 5 means 1. So we're going to think about splitting it so that all the widths are 1. So we say, okay, great. So we're going to split these up. So all our widths, our delta, are 1. And so we can say, well, where do we split it? Just add 1 at every stage. negative 5 halves plus 1, negative 3 halves. Add 1 to that, negative 1 half. Add 1 to that, positive a half. Add 1, positive 3 halves. Add 1, 5 halves. There we go. Now, remember, we always have to pick a point for each interval, and this one is telling us to pick the midpoint, the center. All right, so we need to identify the centers here. So where are the centers at? Well, let's think. What do we have? Well, how do you find the center? One way to do it is you add the two ends and divide by 2. So half and negative a half, add that together, you get 0. Divided by 2 is 0. Oh, that was easy. How about a half and 3 halves? Add that together. 4 halves, which is 2. Divided by 2 is 1. 3 halves and 5 halves, add those, you get 8 halves, or 4. Divide by 2, you get 2. Ooh, these are nice. Nice. Ooh, that's... Okay, how about here? Negative 4 halves. That's negative 2 divided by 2, negative 1. Negative 8 halves, which is negative 4, divided by 2 is negative 2. So our centers are really nice. They're like pristine. So you get kind of nervous, right, when you see the problem. Like, oh, 5 halves. Oh, these could be weird numbers. But it was set up so that the points that we were going to pick were at very good locations. So now we say, aha, we know where we're going to look. So these are where we're going to plug it into the function. These are going to give us where to find our heights. They're not our heights, but it's when we plug those into the functions, that gives us our heights, and our widths are 1. So we say, okay, we're going to take f of negative 2 times our width, f at negative 1 times our width, f at 0 times our width, f at 1 times our width, and f of 2 times our width. So let's plug in negative 2. Negative 2 to the 4th power. Well, it's going to be minus 2 times minus 2 is 4, times another minus 2 is minus 8, times another minus 2 is positive 16. So we're going to have 17 over 1 plus 16. Well, that's really 17 over 17, also known as 1. Negative 1. Negative 1 to the 4th is positive 1. So what we end up with is 17 over 1 plus 1, which is 2. Plug in 0. Ah, we like 0. 17 over 1. So we'll write that as 17. Plug in 1. 17 over 1 plus 1. 17 halves again. Plug in 2. 2 to the 4th is 16. Now 2, 4, 8, 16. And so we get 17 over 1 plus 16. 17 17ths, known as 1. And now we're like, wow, well, check this out. If you have two 17 halves, you put those together, you get 17. Plus 17 makes 34. Plus another 1 makes 35. Plus another 1 makes 36. And there you go. It's actually kind of a nice, clean answer. It worked out really nicely. Now you might notice, wow, these seem symmetrical. Well, they are, because look at the function. It's a function which has symmetry. It's a function called an even function, where it says, hey, if you plug in, say, a negative value, it's the same thing as if you plug in a positive value. And therefore, we should expect there to be that symmetry showing up. That when we plugged in a negative value, same as the positive value. All right, great. Well, we're kind of getting the hang of this. Feeling pretty good. Well, let's do another one. So, our next problem. Consider the following table, which gives information about the function f of x at some points. So we have some locations for x, some values for f of x, there we go. And we want to use this information to approximate the area under the curve y equals x times f of 2x, starting at 0 and going to 3. And we're going to do it using a Riemann sum, 6 equally sized parts, and the right endpoint in each part. Now, this is an interesting kind of problem because we don't know what f of x is, and we'll never know. But in some sense, this is kind of more realistic about what you might have to encounter. It's like, look, I have some data. I have some unknown function, but I know the outpoints at particular points. And now I want to do something with it to help me understand about a process. So somehow finding this area gives us some information, and it does. In particular, information about what the total is. What it represents just depends on context. So you can, when you're doing Riemann sums, be given an explicit function, which is, for example, the last couple we have is an explicit function, or maybe you're given data in some format. Now here, it's data as a table. But the processes are the same. To say, okay, what do we need? We need the widths, we need the heights, which are the function at certain places. In this case, the way we find the heights is we don't evaluate the function, we read the data, the table. It gives us the information. So it's good to be able to be flexible. Say, hey, we can handle things in multiple different ways. All right, well, So let's think about how to begin. Now, I think a nice way to begin a problem like this, since we don't know what we're doing, is to say, all right, let's just think about the interval. We know we're going from 0 to 3. All right, how far apart is it from 0 to 3? Well, we take 3, subtract 0, that says distance 3, and now we need to go into 6 equal parts. Well, that tells us, oh, we're not going to go up by 1, we're going to go up by a half, right? Take 3 divided by 6 is a half. So our data points will be at a half, 1, 3 halves, 2, 5 halves, 3. All right, so there are our points. Now, our delta, our width of our interval, is a half. We have to remember that because that's going to be important as we go forward. Now, the other thing that we need is what? Well, we need to know which endpoint to pick. So that comes from the instructions. We're told to choose the right. So for each one of these intervals, we're going to be going to the right endpoint. Okay, now we're ready. So here's our function, and we begin. So what do we want? We're going to have, for our first interval, we're going to have, plug in a half. 1/2 times f at 2 times a half, which is f of 1, right? Because it's 2 times a half. And then that's the height, right? That's what we get when we plug it in, times the width. Don't forget the width. Okay, keep going. Plus 1 times f of 2. That's what we get when we plug 1 in, times the width, a half. Plus, okay, 3 halves. So that'll be 3 halves. F of 2 times 3 halves is f of 3 times a half. Go to our next term. Be 2 f at 4 times a half. Go to the next term. It'll be 5 halves times f at 5 times a half. And, oh, bad planning. We didn't. Okay, plus, well, we ran out of space. We'll go to the next line. Plug in 3 f at 6 times a half. Okay, so there it is, right? We knew where we were plugging it in, so we plugged in our right endpoints into the expression. See, it's not into f of x because we're interested in x times f of 2x. So you got to pay attention. And now, don't forget that there's this factor of a half. So let's just carefully work through here. So we start with 1. Okay, so we have 0.8. Well, that's times a half times a half. So if we take 0.8 times a half, we're going to get 0.2. Then we're going to get f of 2. So there's f of 2 times a half. Well, that's 0.6 times a half. That's 0.3. Okay, now how about f of 3? That's 1.2. So let's first do a half and then a half. Okay, so 1.2 divided by 2 will get us to 0.3, right? Because if you divide by 2 once, that's 0.6. Divide by 2 again, that's 0.3. And then, don't forget, you have to multiply by 3. So that gets us to 0.9. Okay. Yes. All right. This is a time when it's not so bad to use a calculator. But, in a pinch, you do what you have to do. Now notice the next one, we can actually make it simple on ourselves. See, you have a 2.5. Those will cancel. It's just, what's the value of the function at 4? It's 1.6. Hey, great. We'll just write that down. All right, at 5, well, that's not so bad. See, because we have 2. So if we divide by 2, that would be 1. So f of 5 divided by 2 is 1 times 5 halves is 5 halves, or 2.5. All right, our last one. So we're going to take f of 6 divided by a half would be 0.9. Okay, times by 3 would be 2.7. All right, so now the last thing is we add these up. Yes, let's do that. Well, okay, I'm just going to do that on the side here. This is one of those things where, you might feel like, wow, this is taking me back to old school days. But, the old methods work, right? So let's see, 2 plus 3 is 5, plus 9 makes 14, plus 6 makes 20, 25, 32. So there's a 2, carry the 3. 3 plus 1 is 4, plus 2 is 6, plus 2 is 8. So that gets us up to 8.2. And there we go. There we go. Now, I will say there's 2 places on problems like this where it's easy to make a mistake. One is, the arithmetic. Yeah, it's easy to make a mistake on the arithmetic. I'm not going to lie. But the other is the setup. So be careful with the setup. Make sure you know where are the right points you're plugging in. Don't forget about the width. You have to account for that. And make sure you have the right function in mind. And then with the arithmetic, don't rush. Take it slowly and make sure it works out. I think we're right. I feel pretty good. All right. Well, if I get it wrong, let me know, and we'll fix it later. But for now, let's go on to one last problem. One final problem. This one will actually not be so bad, because we just want to do a little bit of practice with sums, because that is something that's good to know about. All right, so here we go. We're going to write out the following sums. So we have a long list of sums, and we're just going to say what's going on with these. So remember, how do sums work? You see a Greek capital letter sigma, and that stands for sum. Sigma starts with S, sum starts with S. So that's how you can think about it. And now you have to know a couple things. Where do you start? Where do you stop? And what does a typical term look like? So that information, where you start is downstairs, where you stop is upstairs, and a typical term, that's the form. So here we go. So we begin. We're going to start at 2. So So 2 minus 4 is minus 2. Next term will be 3. 3 minus 4, minus 1. Next term will be 4. 4 minus 4 is 0. Next is 5. 5 minus 4 is 1. And then 6. 6 minus 4 is 2. And then stop. Now, we could, of course, find the sum, but it doesn't ask us to. It just says, do we know how to read the sum and say, oh, if we see this notation, this is how it translates. And that's what we're trying to do. So we're good. All right, great. That wasn't so bad. Let's try the next one. Okay, so here we're going to start at 3, go to 7, and the typical thing says we square wherever we're at. So starting at 3, 3 squared. Well, that's 9. 4 squared, and 16, oh no. 4 squared, 16. So that's 3, 4, 5. Well, 5 squared is 25. 6. 6 squared is 36. 7. 7 squared is 49. And stop. We're done. Cool. All right. Well, what's the next one? Now notice here, it uses J and not K. Is that allowed? Yeah, of course it's allowed. We can use whatever symbol we want, whatever symbol is convenient. It's okay to use different symbols. No problem. No problem. So, starting at 1. 1 plus 2 is 3. 3 squared is 9. Next is 2. 2 plus 2 is 4. 4 squared is 16. 3 plus 2 is 9 after we square it. 3 plus 2 is 5. 5 squared is 25. Well, I can do math and talk at the same time sometimes. Okay, so that was 1, 2, 3, 4. 4 plus 2 is 6. Square that, 36. And then 5. 5 plus 2 is 7. Square that, you get 49. And there we go. Now, you might pause and say, there seems to be a connection going on here. And in particular, it's like, what? These two are the same? Really? Well, yeah, because they have all the same terms. So you might say, well, does that mean these two sums are the same? Well, yes. Because again, a sum is a combination of things being added, and if you're adding up the same things, you have to be equal. Now, is there an easy way to see it? And this is just a side note. And the answer is, well, yes, there is an easy way to see it. What you have is this nice correspondence. Namely, you say, oh, this is by the relationship k is equal to j plus 2. So what you can do, for instance, is if you come to this sum, and everywhere you see a k, you put a j plus 2, and reduce it, you'll see it becomes that. I'll leave that as a fun little thing to play with. We're going to come back and do this a little bit more in Calc 2. But for now, we'll just leave it as a side note. All right, well, on to our next one. Okay, wow, more complicated. That's okay. Just be patient, right? So, starting from 0 to 5. So 2 to the 0 is 1. 0 plus 5, 5. Then next term is 1. 2 to the 1 is 2. And then 1 plus 5 is 6. Now you could simplify 2 6 to 1/3. There are good reasons to simplify. There are good reasons not to simplify. For us, our good reason not to simplify is, well, it's not wrong and we're not going to make a silly error. But another good reason not to simplify is if you're looking for patterns. And sometimes what happens if you simplify, you cancel things, you start to sort of obfuscate the pattern that's underlying the data. And so there can be good reasons not to simplify. I'm just letting you know. For us, we're okay with leaving it as is. Okay, so there was 0, 1, 2. 2 squared is 4. And then 2 plus 5, 7. All right, 3. 2 to the 3, that's 8. 3 plus 5, 8. Ooh, that one does simplify a lot. Okay, 2 to the 4, 16. And here, 4 plus 5, 9. Next one, 2 to the 5th, 32. Downstairs, 5 plus 5 is 10. So you can see our exponents do follow patterns of 2. Downstairs, we grow by 1 at each stage. And now we've done 0 to 5. Stop. That's it. Okay. The last one, well, let's figure it out. So start with negative 2. 1, 6 times 1 plus minus 2 over 6 squared plus, go to negative 1. 1, 6 times 1 plus minus 1 over 6 squared. Go to 0. 1, 6 times 1 plus 0 over 6 squared. Plus, go to plus 1. 1, 6 times 1 plus 1 over 6 squared. All right? Now we're up to plus 2. 1, 6 times 1 plus 2 over 6 squared. And finally, plus 3. 1, 6 times 1 plus 3 over 6 squared. Now, this is a case where, okay, you might want to simplify. I don't think there's much advantage to simplifying, so we'll just stop there. And we're done. Now, you see, it's actually not so bad. If you have a sum, well, you just, okay, where do you start? Where do you stop? What does a typical term look like? Okay, then just get going. Start at the beginning and keep going till you hit the end and stop. Why do we have sum notation? Well, look at these two possibilities here on the last one. Which one would you rather want to work with if you had to do it on several lines? The sum notation is so much more compact and it's so much easier to work with. Whereas if we had to write out every individual term, we'd be like, this is terrible. Why are we doing this to ourselves? Which is a great question. Why are we doing this to ourselves? So there are very good reasons to have sum notation. As we might say, it's something useful. Okay, that's enough sum jokes for one day. Thanks for coming. Keep practicing. The more you practice, the more natural the Riemann sums become, the more natural working with sums in general becomes. And it's important to get nice to be able to work with sums because that's what integration is all about. And that's what we're heading to, finding the integrals of things. Well, thanks for coming. Have a good day.